The speaker is Dr. Sprick from the University of Strathclyde. Let's warmly welcome Dr. Sprick to deliver his talk.
Well, good afternoon, and thanks for the kind of introduction here into this talk. Thinking about this earlier, I'm not quite sure how many times I've been to China. I've been around maybe 10 to 15 times to China, but this is my first time actually in Beijing, and it's really a great honor as well. I'm here to receive this award for this paper that was published in Nature in 2020 on behalf of the team. So a little warning maybe here as well from the beginning. I'm a chemist by training, so it'll be quite a focused talk on the robotics side, of course, but I'm a chemist, so keep in mind as well when you ask questions later on as well. Also, I won't use the full hour. I'll probably also sort of finish around the 45-minute mark with my talk in the end. As a sort of introduction, I guess, think about how science and the tools that we use in science have progressed. There's sort of two images from the late 1800s or so from a lab in biology here. You can see people working on wooden benches using microscopes, very typical for the sort of time. You can see it on the chemistry lab as well, some glassware and things and different chemicals being used to do research. And really, in biology, we've really seen a really remarkable transformation of research that's really changed dramatically in the way research is performed. Of course, much more white-hat benches and all these sort of things, and instrumentation. But really what I mean as well, the tools that biologists use are very different nowadays compared to what they used at the late 1800s maybe. So if you take a biologist maybe from the 1800s, 90 or so, and put them in the modern lab, they will not recognize anything of the space and won't be able to do anything in that space at all. In chemistry, maybe there's not so much a case. Of course, the picture is nice and wide. We have really nice bright benches now as well. No wooden bench anymore. We have fumers, which are much more better at protecting us. Health and safety has really improved in these sort of things as well. But in essence, a lot of the glassware and these sort of tools that we use in the lab are very similar. We still heat reactions, we distill things, and so on and so on. So really, it's not the same progression that we've seen in biology. So if you take a chemist from the late 1800s and put in a modern lab, they would be, of course, confused maybe about time travel, but also they would be able to recognize a lot of the things as well. They would be able to do some really basic manipulations as well that we still use today, similar to back then as well. So really, progression is not as fast in chemistry as maybe it's in biology in terms of tools. Why is this important? Why do we need tools in chemistry? There's a lot of really big challenges to be addressed in chemistry, of course. It's really important to make progress in these areas. These are just some of my thoughts on what I think is probably very important to progress in materials chemistry specifically. So thinking about things such as accessing renewable feedstocks as we ramp down oil production, losing access to chemical building blocks. New materials we need, of course, we need much more effective recycling as well. And I'm not talking necessarily about plastic here, I also talk about other materials, metals, rare earths, and so on as well. A lot of things really needed to be changed. Synthesis of quantum materials, superconductors, high power and energy density batteries really still a challenge as well. Safe and compact hydrogen storage materials. We in the UK we are moving a lot more towards hydrogen economy, but actually the storage of hydrogen we have really not solved to the level that we need to. And then, of course, things like CO2 conversion as well into feedstocks in the context of climate change, but again also in the context of just needing sustainable ways of making the chemicals that we need in the future. And then finally, the point here, still the hydrogen production as well. In a way, it's not a solved issue. There's still work to be done in this area as well. And the dots indicating, of course, many other things as well, many things that need addressing. Really important that we tackle these things going forward. I will focus really on hydrogen production in the context of the work. I'll just show you a few slides of introduction into this as well, why we're using the methods that we using in this sort of approach here. Hydrogen production is really quite established using PV and electrolysis. In Scotland, maybe not so much PV, much more wind power, but we can use renewable energy and use an anode and a cathode to do reactions there, producing hydrogen sustainably. But the efficiency being very high is great. These systems really work. They also are somewhat on the more complex side, and the cost actually of these systems is still relatively high as well. researchers really focus on alternative methods such as photoelectrochemistry. So we irradiate here one of the electrons at the same time as well. These systems are less efficient, but in principle they are somewhat less complex, but they are potentially on scale much cheaper. Our research, though, really focuses on using photocatalysis, really quite simple. You can imagine large tanks of water, perhaps, where we add powders, and these powders spontaneously, with sunlight, split water into hydrogen and oxygen. So really quite simple approaches, which also could make these approaches really quite cheap in the future. But the challenge, of course, being the efficiency is still relatively low. So we need to improve on the efficiencies of these systems really dramatically. Let's give you one of some examples from the chemistry side. The details are not too important. Just to highlight these, the approaches being taken. This is sort of structure here, quite a simple structure that was used as early as 1985 by a scientist in Japan, Shonzo Yanagida, really pioneer in this area. But he sort of worked too early on these projects. In the 80s and 90s, there was enough oil and gas available, no interest in really funding his research. And we took this up in recent years, these structures, and modified them because we are material chemists. So we thought maybe we can introduce these blue rings here, and this, for many reasons, should make these materials more active. And indeed, we find that these materials are more active. We can see significant improvement of the activity in this case here, so 15x or so improvement. And of course, we can think about other modifications as well. We can maybe put this red ring in here, do some other thing as well. And for many reasons, we would expect this to work better as well. But indeed, we find actually it doesn't work at all, really inactive material. Then we can maybe change the structure quite dramatically as well, put this unit in here and see what we get from that. And we get really nice improvement in terms of activity of all these systems. 51x, really, really good systems. And, again, thinking about the structure, maybe we can modify this here as well and get this structure. And for many reasons, again, we expect this to be better. But indeed, we find actually it doesn't work nearly as well. And we spend a long time sort of looking at the space for this sort of iterative method. And I think we can say with some confidence that really iterative design has quite severe limitations. So this approach gives us some results, but we're really not able to find sort of a breakthrough in the sort of huge steps up in terms of research efficiencies here in this case. And this, of course, is because these processes are really quite complex processes, multi-length scale complexity. I'm not going to read all these points here. There's many things that these systems need to do on the chemistry and physical chemistry side. And the problem really is that these are things that work together as well. They are sort of factors that are interlinked. Thus, we are not really able to design materials from the atoms up. We can't just think of a structure for thinking that these structures might have these properties, and therefore this will work much better. It's not the case. We can't do it. We really need to have other approaches. So another approach that we took then, as a later publication here, you can see, was to just screen spaces. So we have something that's quite modular in its approach, and we can use a high throughput microwave system to do many experiments in a very short time. In this project, the student made 128 materials in the study through really rapid synthesis, and he was able to purify them and test them as well. And indeed, we find that one of the materials here, as an example, works really much better compared to this material here. So there's some gain here. We get activity, and the activity of the system is higher compared to what we have found previously through a much more iterative approach in this case. Apologies. Well, of course, this in itself is not really that interesting. So we thought about this a bit more, and how can we maybe analyze the data a bit more to gain a bit more insight into these systems as well. So we looked at the energy levels of the material. We looked at how well does the material absorb light. We looked at how well does the material interact with water. And we plotted this against the hydrogen evolution rate, so a measure of the activity of the system. What we find is, when we split the population in the top 50 and the bottom 50%, that the top 50 best performing materials are really quite sharp in this sort of area here for one of the energy levels. They're relatively sharp as well here for optical gap and turbidity. But of course also the bottom 50% sit in a very similar space at the same time as well. So it's really questionable if we really learn much from this. So based on that, collaborator at UCL, Martin Sweinenberg, and the postdoc Liam, they looked at this, the whole data set, and what they performed was this machine learning where they have this leave one out cross-validation approach. So using a whole data set except for one material to train the system, trying to predict the hydrogen evolution rate, and then we can plot this as a function of the observed hydrogen evolution rate. And using 4 descriptors here in this model, we can get a fit of around 68%, which, thinking about this, is really quite good. We have only 4 descriptors in this model, really quite a simple description, and it's really, quite a good match. But of course, it's really far away from 90, 95, or 99%. And this is probably also because of factors that are missing, things that we haven't actually measured. And I guess the bigger problem with this approach is overall that the system is not forward predictive. It really only tries to explain data that we observe and the variation of the data that we observe. So the question is like, how can we screen such complex spaces and also be forward predictive in this space? And really quite clearly, we need new approaches, new methods to do so successfully, because this space, as I said before, is really quite complex with many factors affecting the activity of these systems. So instead of just screening materials, well, how about we go more towards a closed loop experimentation, whereby we still need chemical knowledge that we feed into the system. We use language models and computational design to inject the knowledge into the system. And then we use robotics, AI, and data handling to analyze the data and make suggestions going forward as well to design better materials as well. To enable this sort of automation, of course, would be very important. And there are systems in chemistry that enable automation at really sort of fast speeds on significant scale as well. There's an example here by Strateos, as well as ChemSpeed here as well, and based in Switzerland. These systems are, they are really fantastic, and they're really quite a lot used in chemical industry as well. However, they also are very bulky, very expensive to purchase, and also they're not really as modular as we would like them to be. You set up these systems here, you can see these the units here, and modifying the workflows to do other things is really quite complex in these systems. So the flexibility is really lacking on that in these systems overall. So instead of doing that, how about we do something else? And if we consider that the scientific instrument market is really large, there's lots of instrumentation available worldwide. Here's some sort of typical examples of that I took from the internet. They are all designed to be used by humans. They really look like machines that a human would interact with. They have buttons and displays, and also the scale and so on is really made for humans. So humans can really easily interact with these things, of course. They're made for humans. How about then if you automate the researcher and not the instruments themselves? So quite a different approach to ChemSpeed, for example. And I hope nobody from ChemSpeed is here. This also would potentially be much, much cheaper than compared to ChemSpeed as well, because these machines are really, really expensive if you buy commercial systems. So the idea behind the system that it's autonomous and mobile, it can maneuver in space, and really key thing here, it's a sort of designed as a drop-in solution. We can make modifications to the lab space that we have. There's some modification needed for this, but overall, it really can be almost dropped in that space. It needs really little modification compared to commercial systems. The system here we developed things in multi-dimensional spaces, and Andy Cooper liked this phrase. He did a PhD in a week. I slightly disagree with that notion, but still, it's really a rapid system to do experimentation in this case. See here the actual lab in which the experimentation was performed. That's really the first example of a mobile autonomous robot scientist. The units down here, that's the lab space. There's a software up here that's used to maneuver within the space. It's used LiDAR to recognize positioning within the space, which also enables it to work safely within the space here. There's a charging point I will point to later on again. And it has this arm as well, which is a bit hard to see maybe now, which allows the robot to interact with really common lab equipment in this case as well. So we can really replace a scientist with a robotic system which has an arm that uses instrumentation just like a human would be, almost. There's been really quite a lot of media interest on this as well. You can see here sort of articles in popular newspapers in the UK, The Times and The Independent, and of course we were particularly pleased that this also went into the Daily Mail in the end. But also popular, the news as well picked this up as well. There's a BBC report looking at the project as well. Really a lot of interest, really a lot of attraction in this area. And I have to say also, the interaction with the media was actually very positive as well. Like normally, robotics and AI, there's a lot of skepticism and sort of fear of loss of jobs and so on. The interactions we had were actually really positive, which I have to say was a really, really good thing in this project. That's Benjamin who actually led the project as well. Right, so the system, how it works then is we have different stations, and these stations are really built based on commercial systems, commercial lab equipment. We've got a station that does solid dispensing, so we have a photocatalyst, in this case, that can be dispensed into the vials you can see here as well, and it does so automatically, and you can see it's a Mata Toledo system, really a commercial system that's used in many labs around the world. Then also we need liquid, of course, we need water for water splitting. This system here handles liquids dispensing, and this is more of an in-house built equipment, but really all the parts are also commercial parts that we could buy from really standard vendors as well. And using the balance here, it's able to weigh out liquids really accurately as well. There's also another station here in the background as well, which the only part really that's sort of custom built for the project to degas the samples, which is really important for the quantification process. We had to have some special machine made, but the other ones are all really commercial systems. For the reactions themselves, we have this block here where the samples are put into, and then it's irradiated from the bottom using an LED. Again, parts are commercial. And then for measurement, it's really a standard gas chromatograph, which allows quantification of hydrogen production in this case here. And one of the curiosities of the system was really that the robot, you might have seen it here somewhere, actually has to press go on the GC as well. We weren't able to automate the system. I think it's doing it now maybe. It wasn't able to hack the equipment to do it remotely. It had to be the robot pressing the button. So it's really truly a scientist pressing the go as well. Right, you can see here that's how it then operates in space. It drives around in the space and does manipulations going through the different stations. And again, I just want to highlight this as well. It's safe with humans in there as well. It recognizes humans being present, and it will avoid collisions and so on. So it really can be co-occupying the space and co-working in the space with the scientist as well. This is the sort of actual setup, how it's used in this case. We have the stations here, the solids, the outweighing out of the solids, the liquids here, and this is capping machine, as I mentioned before, the only really system that was not commercially available but bespoke made here. Then the GC station over here, that's where we fertilize the samples. This is racks in, so the racks are printed racks with a 3D printer, with vials, which robot can interact with and take and transport to the different stations. And then at the end, it also disposes of the racks here once the experiments have been concluded. You can have a look at this here, how it's sort of run through the experimentation. Then it goes between stations. It finds the optimum path between stations as well, making sure that the stations are as busy as possible. And also it goes to the charging point here in the middle somewhere as well to recharge, again, trying to minimize downtime during the experimentation as well. And of course, it can go through the samples day and night. Actually, you see here as well, this footage works on a Saturday here. So really, days in a row without interruption, performing constantly experiments, optimizing the experimental space and finding better solutions in this case. So what we actually did in terms of experiment then was to look at one specific photocatalyst, we call it P10 in this case here, which makes hydrogen, and in this case it oxidizes cysteine, so a naturally occurring renewable feedstock for the oxidation side. We used the sort of space to explore it. This reaction works, but we really want us to see, can we really make a huge improvement in terms of activity by using sort of 6, what we call here, loose hypotheses. So things that might improve the activity, but we're not really entirely sure in this case, maybe. Some of these things, of course, are really obvious and they should make sense, like including the sort of best catalyst loading. Other ones, such as changing the dispersants and adding these H bonding anchors, really unsure whether they actually make a huge difference. And it's really enabling to have this sort of ability to test like much more loose hypotheses as well, because otherwise we wouldn't really test any of these. We wouldn't really steer away from them. And of course, when we combine all these hypotheses now, which are interrelated as well potentially, so there could be some sort of synergy or interaction between different hypotheses, we get a full simplex of in excess of 98 million. So as a human, you would never really go through the full experimental space. You'd be really selective in trying to sort of look at things. And some of these things, as a chemist, I would say, I'm not really sure they're worth trying. They're probably a complete waste of time for an actual scientist in a lab to do, because the chances of them working are really quite low and remote. So the system then uses a Bayesian optimization strategy, trying to get an optimum space here, trying to get the best performance out of the system. And the search is performed in batches of 16. Why? Because it's the sort of sample folder that we have available for the experimentation. So it uses the optimization to optimize the space and then make suggestions based on that for the next experiment it wants to perform. You can see here sort of 18 runs or so of this experimental space, changes in color as the components used in the experiment have changed over time. One thing I want to really highlight here, this is works for catalysts, what we call formulations, so mixtures of things. What we can't do with the system is chemical synthesis, and it's really quite an important distinction. It can't make new things, it can only mix known things. The challenges as well are there's really no underlying chemical descriptors, so it really relies on setting limits. As a chemist, you have to set limits for the system where the space you want to explore in terms of amounts and so on. And really key point as well, these systems don't understand chemistry. So really, going forward, we have to still have a chemist there as well to think about safety, for example, or maybe things that are completely nonsensical to sort of take them out because it might cause other problems for the system in the end. Then, sort of looking here at the actual run, how this operates. As I said, we have 98.4 million possible combinations with these factors. And then if we leave the system running, it did run here over 8 days or so through the space, varying the search space over time. You can see here compared to a baseline, so that's where we really started in terms of what we knew would work. I can see that we have a huge increase in terms of performance over time. So really getting optimized system out of this through autonomous discovery in this case. At some point, the system then found it was sort of stagnating, wasn't really much improvement, and that's also when the system made a suggestion to stop the experiment here, and that's sort of what we take as the sort of best performing point here in the end, the optimum formulation in this case. If we're looking at individual components that were in this mixture, you can see here that of course the photocatalyst, which really drives the reaction, is required. It's present in all these samples, but also we actually set a limit as well. We said we don't want this not to be included. It has to be always present in some amount. Cysteine, so the thing that the system oxidizes, is always present as well. But also tried a few times what happens if we have no cysteine present in the experimentation. And these things here, the sodium salicylate and sodium hydroxide, also varied. But in all cases, it was selected and deemed to be important for the experiment. We're looking at here at Some other things, sodium chloride, for example, was a suggestion at the beginning, something that was worth maybe trying if you have the ability to just try different combinations, but the system decided to deselect it. It doesn't really help, it seems, with the activity of the overall system. Similarly, surfactants, so things like soap-like materials helping with the wetting of the system, were also pretty rapidly deselected and were found to be less important in these systems. And equally as well, adding dyes, where the thought was that these might help us to absorb more light, because if you absorb more light, you get a better system that converts light, of course, as well. That was found to be really deselected quite rapidly as well. But interestingly as well, the system went back at the end here and tried these one more time as well. But really, it was deselected and not in the final material formulation that we used for the experiments in the end. Interesting to see as well is the interaction between components here, and there's really chemical knowledge here. Sodium salicylate and sodium hydroxide, there's sort of a strong interaction. This sort of area, specific ratios were found to be really, really good in this case in the mixture. And I guess there's some sort of intuition as a chemist as well. This sort of makes sense to have, but the exact ratios and in the presence of the other components were really not clear to us what would be the ideal scenario. So really enabling us to find the optimum for this here as well. Then of course, we have to also validate these results. These experiments were performed by the robot on a station that used LED light. LED light is very different from natural light. You can see we have a significant improvement, but of course we also want to test using simulated solar light. And indeed we find actually that the system still shows significant improvement as well in terms of performance if we use a solar simulator. Maybe a little bit less compared to this system here, but this might be just a function of optimizing more for the LED, not for the actual application. So something to think about going forward as well. How can we match it more onto natural sunlight in the end? In terms of like using time and space in an optimum way, if you think about performing 1,000 experiments, if we do this manually, a researcher would use the sort of setup here, setting up an experiment, then after that performing the measurements and quantifying the sort of result, and then think about like the next experiment to be performed. You can see here we got this sort of approach here. If we look at a semi-automated system, that's a system we used previously, but it's a chem speed system. We can do things in batches really. But again, in batches also means we have to prepare and then test and so on and so on. The robotic system is really autonomous, only it's set up at the beginning and then runs from there to do all the search in the space. And what it really means, like we can really reduce the time. Manually, maybe we can do one experiment a day or so. Semi-automated, we can do many more experiments, so bringing down the time to 5.5 days. But the autonomous system, because it just works constantly, we can bring the time down to half a day of researcher time, and the system can just perform the time on its own. This again frees up time for us to do other things which are maybe more interesting or more relevant to our work. So I guess it's sort of a question then, does it bring us back to a golden age of discovery? There's a sort of work here by Giacomo Scimian, who had lots of reactors on his rooftop of his university to do experiments, chemical experiments, and it was really quite inspiring to see this sort of approach back then already. But we can't really afford to do many of these things. Our totally speculative experiments are just deemed very risky. There's really quite a lot of push and drive to get results these days, because you need to publish papers, we need to progress with science. So like using this approach, screening is really risky, speculative experiments is really risky. We need, in our space now we have very limited design rules, thus we can only really get incremental targets, thus we can only get limited increase in performance as well. So really need a step change. And we sort of really hope that the automation really enable this going forward, that we can really do a lot more things in the future much faster as well. And ideally, of course, we would go to having really closed loop discovery as well. So instead of just looking at formulations, we would think about structures as well, materials, optimize them and their space as well, feed them into the measurements cycle whereby we do the measurements of formulations as well, optimizing the performance, but then you can also use that to feed back into making new materials as well. And now, this would give us the best of both worlds, constraining the search space without prohibiting surprises. And again, like, it doesn't really remove the scientists. It's really important that we have still input here as well. First and foremost, of course, sort of ideas, but also things like health and safety will be really, really important going forward. So hopefully, sort of in summary, I've shown you that this robotic scientist has really enabled the development of workflows that can be used to use cheap equipment from commercial sources to really enable high throughput and screening of materials. It really sort of demonstrates the making of formulations, so mixtures of compounds for catalysis. But really, there's a bit of a way to go towards chemical synthesis systems. So like actually making materials rapidly, still there's some challenges to overcome, which are currently also being still studied in the laboratory in Liverpool. Think about the lab of the future. But there's really, there's a long way to go, somewhat. Still a lot of challenges there, so really a lot of space for scientists as well to contribute to that. And with that, really I want to thank, first and foremost, maybe the selection committee for selecting this paper for the award, the organizers of this conference, many people that worked on this project. Really, it lives off the collaboration between scientists, computer scientists, people that work in automation. Companies here have been quite instrumental as well in helping. Then, of course, I thank these guys here for funding, and thank you for your attention, and happy to answer any questions you might have. Thank you.
Thank you, Professor Sprick, for sharing his work. Now we have some time for questions.
Hi, Sebastian. That was a very great talk, right? So I have 3 questions actually, right?
Sure.
Or comments also, right? So number 1, have you considered like swarm robots? Because now you only have one robot going about, right? So if you have like a swarm of them collaborating,
yes.
will you get like more data faster, right?
Yes, of course. That's actually exactly what's happening in Liverpool. There's more robots. I think there's 3 at the moment actually looking at wider space, also like sort of different activities as well. So it's not only around thinking about optimizing performance, also thinking about like studying stability of systems, for example, is very important as well. Like not just having more of these systems was really instrumental in pushing this area forward. Absolutely.
Okay, thanks. The second question is actually on the optimization. So I saw that you're using Bayesian optimization, right? Have you guys considered like evolutionary algorithms, for example, like genetic algorithm or like particle swarm algorithms, right? Why I'm suggesting this is because, right, this kind of algorithms, right, are heuristic in nature, right? You can actually explore, like quite a lot of them in a very effective way too, right? So, yeah, have you considered that?
I mean, this is a paper from 2020, and obviously it has moved in that direction. Absolutely. No, it's like there's a lot of innovation in algorithms and so on, and like of course, yeah, it has moved into other areas as well, really exploring other algorithms as well. Yes, very, very correctly saying that.
Okay. Yeah, the third point is not really a question, but like a suggestion. So I think that your robots have actually collected a lot of data now, right? So I think that's great. So have you considered like using this data to train a neural network, right? So that in that case, right, you don't really need extra data, but rather your neural network, right, can kind of predict what kind of outputs they can have if with certain inputs, right? So if you can do this, then perhaps you can do the optimization even faster, right? To do that, and like you have nothing to lose, right? Because like based on this model, right, whatever formulas that they gave you, you can just ask your robot to do it and just try whether that really works or not, right? So yeah, I don't know whether you have considered that. Yeah, thank you.
Okay, well, thank you. I'll pass it on. Thank you.
Thank you.
Thank you for the talk. I just wondering, did you consider what is the input starting point for the system? If you give the system, say, a formula or give it something like what you want to do you consider to combine with the large language model? Say, I just give this robot paper and let it read by itself, and then after say half day, and everything is done, something like that.
So, okay, in a way, there's some work actually happening in this sort of like screening the literature space, looking for new ideas. I guess that's sort of where we're going, isn't it? But in terms of setting up the robotic system itself, we are still restricting it somewhat. We still have to be in control in terms of what it does. Again, health and safety is a really important consideration here as well.
But for the optimization, if you only based on statistics result, I don't think it will give you the best. Maybe this guy has suggested the AI.
Yes. Yeah.
Or yeah, I just wondering, maybe in the between it can be improved.
Sure.
Thank you.
It's something to think about. Yeah, absolutely. Thank you.
Oh,
Yeah. Sorry, I keep on asking questions because I'm really excited. So let me just share something with you. So people are talking about smart factories now, right? So understand that you want to create a mobile robot that can be more flexible and adaptive, right? Right. But that's what smart factories are moving ahead. But at the same time, people are also talking about once you have this kind of robots, they might also want to do like specialized kind of stations to help the robot. So like the stations now the robot is going through is like really, for humans. Am I right to say that, right?
Sure.
Right. But you can also consider in the sense that this kind of devices can be, changed or modified to suit your robot better too, so that you can actually have the best of both worlds, right?
Sure. But I guess the explicit point of the project was really to access current space and current instrumentation as well to some degree. Really enabling it to do a greater variety of things. Now, this is a specific project or hydrogen generation from water. What if we want to move to something completely different? It's much easier to use standard off-the-shelf equipment in that case. That's sort of the motivation of it.
Right. Understand. But I think that I don't know. I mean, I think this can be something exciting and potential avenue to explore in the future too.
Sure.
Right. Because actually, people in the smart factories have been discussing about this quite a lot, right? And they're also open to create this kind of specific machines that can help the robots, right? And that can actually help a lot, actually, potentially, right?
No, sure. And I get it. It's just like the sort of idea behind this project was really the flexibility. In Liverpool, so where this work was conducted as well, there is large-scale automation as well. There's a formulation engine, but really it's around the flexibility and then changing direction really rapidly as well, which is motivating this work. But thank you for your comment, anyways. Thank you.
Okay, thank you.
any other questions? Okay, if there is no more questions, so let's conclude this talk, and thanks again, Dr. Sprick, for his talk, and thank you all of you for attending.